Good evening and welcome to Adventures in Particle Physics, coming to you live from the University of Stavanger in Norway. My name is Alexander Rothkopf and I will be your host for this evening. This week, the Institute of Mathematics and Physics at the University of Stavanger is hosting a virtual physics conference with more than 300 participants and more than 150 presentations on new scientific findings in experimental and theoretical fundamental physics. This research is made possible by your taxes, and we are aware of the responsibility that comes with your trust. And as scientists and teachers who wish to share with you what kind of physics research is actually discussed at this conference. And to do so, we have prepared three inspiring presentations for you this week, one this evening, then a second one on Wednesday, August 4th, and the third one on Friday, August 6th. The speakers are all physicists who wish to share with you some of the insights and the fascination they have on studying the smallest building blocks of nature and the forces that tie them together. Yes. And whenever you have questions or comments during the presentation, please make sure to leave them in the live chat window that is right next to this YouTube video. I will be collecting your questions and comments, and we will get back to you together with the speaker at the end of the presentation. So stay tuned until the end of the presentation for a question and answer session. Our speaker this evening is a veteran in experimental particle physics. His name is Eckhard Elsen, and until last year, he was the director of research and computing at Europe's largest particle physics laboratory, the CERN Laboratory in Switzerland. Norway has a strong connection to CERN as it is one of its founding members, and CERN supplies around 2.3% of the annual working budget of the CERN Laboratory, amounting to around 290 million Norwegian kroner. And these funds directly support also research at Norwegian universities, with researchers there collaborating and working together with the experiments and theorists at the CERN Laboratory. During his career, Eckhard, as it is custom for successful physicists, researchers, has worked at many different international laboratories, for example, the DESY laboratory in Hamburg, Germany, or the SLAG laboratory in Stanford, USA. And during this time, Eckhard has not only worked on existing experiments, but he has been developing and planning new and future experiments. And since 2006, he has been professor for physics at the University of Hamburg, where he's then educating the next generation of physicists, bringing to them the direct insight and experience he has from fundamental research. And tonight, Eckhard will be telling us about the ongoing mission and the successes of the CERN Laboratory that he helped manage for several years. And with that, please, Eckhard, the virtual stage is yours.
Thank you, Alexander. I have to adapt to this virtual mode of giving a presentation. You can imagine that I would love to speak to the audience live. Maybe it's a little bit like the Olympic Games that happen in empty stadiums. I will try to give you a brief overview of what CERN is doing. Just to repeat, my name is Eckhard Elsen, and since the beginning of the year, I'm back at DESY, but it's of course a pleasure from my side, to show you some of the details and aspects of CERN. And I will not only discuss science, but I will also give you some demographics, the users, so that you get a feeling for what Norway is also contributing to this endeavor. For those of you who have not been in Geneva, and for those who have been, the yellow circle shown here, of course, you will never see from the plane. It's 100 meters below ground. Typically, that is the tunnel of the LHC. It's next to the Geneva airport, the little strip you may be able to see here, and close to the LHCb experiment and the Lake Geneva behind. So the Large Hadron Collider tunnel is actually housing the counter-circulating beams, protons and protons, that then intersect each other at the location of the experiments here. So I will mostly speak about this largest colliders, but of course, CERN itself commands a larger spectrum of accelerators and tools and even decelerators, as I will allude to. So what is CERN actually? When we look at the mission of CERN, it's clearly science. So to push back the frontiers of knowledge, and we particle physicists are quite ambitious here, namely to understand the secrets of the Big Bang, the big explosion, if you wish, that created our very existence. But what was matter like when everything was basically contained in a point? We try to unravel that, and the tools with which we do that, I will describe a little. You see the photograph of Albert Einstein alluding to energy E and mass M that are intimately connected there. In doing so, of course, we need the most advanced tools, accelerators and detectors. And you can imagine that none of them can be operated without using very advanced computing tools. The web that we use every day, several times, many times, originated from CERN. And the grid, in some sense, what we call grid, is the precursor to cloud computing that also has become commonplace. Now, the tools developed at CERN also help other fields of science and technology, and I will give an example of medicine in which the tools, accelerator and detectors are used to actually diagnose or even have aid in therapy. The other, and maybe the most important element of CERN is to train the scientists and engineers of tomorrow. Make sure that they are really at the very edge of the knowledge today, so that they can take our knowledge and research further into the future. And we don't start from the past again and again. And since CERN is an international, initially European laboratory, it unites people from different countries and culture. And that in itself is a very important aspect. It may be the most important in the beginning, because CERN was founded in 1954 by 12 European states, and basically to enable science for peace. At that time in 54, several European states had started to launch a nuclear physics program. They also had started to build smaller accelerators, but then realized if we really put the money into one pot and build a European laboratory with no limitations on the publication of science. So make it very clear from the beginning that the science that would result from this endeavor would be available to everyone, so that there is no misuse of what comes out. Science for peace. That was actually the motivation to get together. Today, the number has increased to 23 member states, and below you see a list of the member states, mostly European, with one notable exception, namely Israel. Well, it's close to Europe, but rather in the Middle East. This is because the Israeli scientists were so engaged in CERN from the start, not only in CERN, but also in other European countries, that they were basically considered European in this list and joined. Member states are the countries like Norway who contribute a certain share of their net income to CERN, such that the overall budget is 1.2 billion Swiss franc per year. It's only slightly complemented by the contribution of associate members, for which we have two categories. One is associate members who are in the pre-stage of becoming full members, and you have Cyprus, Estonia, and Slovenia in this list. And associate member states who contribute less, have less rights, but nevertheless want to engage in the physics of CERN. And here you have a list that I extended only today because Latvia joined as of today. So there is a new associate member at CERN. And then there are observers to CERN, to the CERN Council. These are countries like Japan, Russia, and the United States of America, who entertain a very lively physics program of their own. So did not consider joining CERN as a full member, but want to participate in a particular aspect of the CERN scientific program, which is the LHC. And so they will join council sessions for whenever there is discussion on the LHC or its future. And then there are European bodies like the European Union, the Joint Institute of Nuclear Research near Moscow, and the UNESCO, who join because of their wider interest in Europe to support science in general. So as we enter this talk, and before I show you the rest of the slide, I give a disclaimer here because the demographics that I will refer to evidently refer to the year 2019, which was the last year not affected by COVID-19 pandemic. It would not make any sense to give you the figures of 2020 or this year's because the number of visitors clearly is almost zero, not quite zero, but it's not in any way representative. So the users' presence at CERN has been severely restricted since March of last year. It went up and down a little bit, but basically CERN was blocked for visitors, and only those who had to work without any way of home office, they were at CERN, and even not at all times. The situation is improving like everywhere in Europe. CERN is currently in the COVID level 2, which is the yellow level, color-coded scheme, which means there is CERN is opening up to some extent. And for visitors, maybe the best way of looking at it, it's like the Geneva museums that need to ensure limited occupancy and proper COVID protection measures. But I'm just indicating here that CERN went through the same story that most of us went through in our other jobs. So with that disclaimer, let me briefly speak about the science, and I start really in a broad picture, namely our motivation is to understand the very first moments of our universe after the Big Bang. Now you will ask, well, why don't you just look at the signals that come from the Big Bang? Well, there is a subtle reason, because at the time of the Big Bang, the universe was so dense that there was no way for light to escape during this completely opaque phase. So since then, 13.8 billion years have passed, or with the speed of light, 10 to the 28 centimeters have the universe has extended. So today it is much larger, and what we can do is, for example, look at the microwave background in satellite experiments or on Earth to detect the light signals, the electromagnetic spectrum that originates from the early phase. We get a lot of information from that. And this is just to illustrate a little bit. This is the radius of the Earth. So we are somewhere here in the meter scale or so. And the size of the universe goes out here, and we observe it with a telescope, be it ground-based like the ALMA telescope or very large telescope, or from space with a Hubble telescope that is known to everyone, or with a particle physics experiment in space attached to the ISS, the International Space Station. And we get formidable pictures of the universe, like the one here, where you see the galaxies and the stars. You notice that the spectra of particle emissions is redshifted. So we learn about the expansion of the universe and quite detailed knowledge. Now, with the information we derive from that, our appetite is just increased to look further down. When we get to the size of atoms, to the size of nucleons, protons, for example, and then even much smaller scales, well, we would easily love to cover 60 orders of magnitude as is done on this scale. But it's not easily possible because, as I illustrated before, we had to wait until the universe cooled down to a temperature below some 3000 degrees or so, the temperature of the sun, so that we would really see the light emitted from that period. So the period of 400,000 years or so after the Big Bang is completely excluded from our detection. And that's, of course, where a lot of fast expansion happens. Physicists call this period the inflationary universe, when the expansion was very rapid. And so we want to understand more about the forces there. So the only way, since we can't observe it, is to recreate the conditions that existed at the time of the Big Bang in the laboratory. And of course, we can't go back to the very first nanosecond, but we can move back in time a little bit by using a super microscope, which is the LHC, in which we create energy densities that roughly correspond to this period. And the LHC is able to do this, and when we collide protons stored in the LHC, we reproduce these conditions, and then we use theory to come up with a rationale that would explain the universe as it looks today, and we observe it in telescopes. So if you wish, with the laws we established here from the observations in the super microscope, we could run simulation, and then our universe or a similar universe should emerge, which today is governed by the gravitational forces that give us the universe with the stars, the galaxies, or the planet Earth surrounding and circulating around the sun. So this is the bold game, and the question is, do we understand these initial forces so that we can easily transition, for example, through computer simulation that know about the rules to the universe that we observe. And here's a bit more of the tool we have, the Large Hadron Collider, as I told you, 100 meters below ground. We have superconducting dipole magnets, the strongest magnets we can build, to bend the high energetic protons around the large circle with a circumference of 27 kilometers, which we then, and we have counter circulating beams in this stored in these magnets. So we even have magnets of opposite polarity that keep the circulating beams on track so that we can collide them at the 4 interaction points depicted here. And at the interaction points in the middle of these detectors, you can see them here, we put the high resolution detectors, which are not tiny, but they are also tiny. So we will go as close to the interaction point with small detectors. And then as the emerging particles, remember Einstein, energy equals mass. So we generate other massive particles that emerge from this interaction point. And by recording their trajectories as they exit from the interaction point, we can calculate back to what happened at the interaction point where the proton collided with a proton, and thus can understand which forces were in place when the particles collided. We have various particles that are command protons and protons, or protons and lead. This is the chemical symbol for lead. So we can have heavy ions colliding with protons. That's a bit of an unfair collision, as you understand. Lead is very heavy and proton is just a proton. So you will understand that in this case, the proton is very tiny probe into the lead ion, or we can have counter-circulating lead ions, and the lead ion contains 208 nucleons, protons or neutrons. So it's a heavy object. It's a massive object colliding with a massive object. Energy densities that are unheard of, for which we can then study the strong interactions. And the dedicated experiment, the ALICE detector, focuses on that type of physics. The other two detectors, ATLAS and CMS, are general purpose detector, looking at the wide spectrum with some restrictions in their detection capabilities. And LHCb focuses on what we call the forward direction. This is when the particles are scattered only at small angles, which is also of particular interest. So this gives you the experimental scenario. With these high energetic collisions, we need vast detectors to record the particles. These are the instruments, and now how do we operate these instruments? And this happens in a very global fashion. And it's shown here by showing the distribution of the CERN users by the location of the institutes. And you see in the dark blue, the European CERN member states. In the lighter blue, the countries that are aspiring to become members. And you see, I haven't been able to update the list for Latvia and Lithuania, or now or have become associate members. But what you also see is that there are these green countries, Russia, US, and Japan, who are observers to the CERN Council. And you have these red dots in which scientists from institutes in these countries participate in the experimentation. So they don't build the accelerator, they don't contribute to the construction and expansion of CERN, they don't contribute in deciding on the CERN scientific program, but they participate in the large detectors. And when you compare the numbers or look at the numbers, we have something like 7,000 users from the member states. We have 3,000 users from the observers. With the US, who are contributing to the LHC, is 2,000 users. So in a way, CERN is one of the biggest US laboratories in the world. But you also see some 1,400 users coming from everywhere: Australia, South America, South Africa, and so on. Unfortunately, the middle of the African continent is still rather softly populated. You can also look at nationality, because nationalities, scientists may be employed in other laboratories. So here you see a different coverage of the origin of users, with some encouraging signals also from Africa. South America is almost entirely covered. In fact, all the entire globe is colored in one way or other. So people come from all nations to participate in the CERN program. And this distribution, I think, is maybe the most important one, because typically when you have an employment curve, you go for sort of a rectangular box. You hire people at a young age, and people then retire at the age of 65, and so you see the step function here. But for CERN, it's different, because this peak here at 27 doesn't get older. Well, people do get older, but there is a constant population of PhD students at CERN who come and spend typically a year at least at CERN to carry out their experimental program. Then they go home to the university, to Stavanger, Oslo, Bergen, you name it, and then complete their thesis at home. And this is really the lifeline of CERN, because you have always fresh ideas coming fresh from the universities to try out new concepts at the experiments at CERN. New analysis concept, new computing concept, machine learning, to give you one buzzword. And it's very important that this happens so that the science at CERN remains young and lively. It's of course obvious that few of the people here in this population remain forever at CERN. They go back to universities, they go back elsewhere. In fact, where do they go back to? Roughly half of them go to industry, and then you have universities, research institutions, or governments for advice, or to other. They may found a company of their own. What fields of science do they go to? Computing is an important element, consulting, physics, engineering, and even finance. You can imagine that with machine learning and Monte Carlo methods, these people are well versed to also enter optimization problems in the financial market and communication, and you name it. So you see, CERN is not only feeding a lifeline for physics, but it's really a broad field of academic work, and then activities in industry and research in general that is enabled by people working at CERN. Some of them, of course, stay at CERN, and that's also important. Now, the science, of course, I'm sure you're familiar with the result that led to the Nobel Prize in Physics in 2013, namely, finally, after a search for 50 years or so, the discovery of the so-called Higgs particle, which was then mentioned in the laudation that the two theoreticians, Francois Anglaire and Peter Higgs, received for the theoretical work that was done in the 60s, and then led to the discovery of the Higgs particle in Atlas and CMM. And I will come back to the significance of that discovery later on. But before embarking on the physics further, let me speak a little bit to the point of view of science and technology. Because when you engage in fundamental science and research, you have to use the most modern technological developments. Often you have to develop them on your own to enable to break the frontier and make a step forward. So technology is most important. And some people even call CERN an engineering lab rather than a physics laboratory, because the physics is actually carried out by the users that come to CERN, the 12,000 or so that I mentioned before, whereas they receive excellent engineering support at CERN. And the engineering support covers actually building accelerators. Very few universities engage in building accelerators on their own. There's some more who teach courses of accelerator technology. So that's a home domain of CERN in some sense. Detecting particles or building detectors is something that is more widely known in institutions, and many institutions engage in that. And then, of course, these detectors and accelerators are operated by computers and read out by computers. So large-scale computing is something that happens all the time at CERN. So let me speak to computing, how it was conceived in the first decade of the century, when the worldwide LHC computing grid was put in place as a consortium between many countries, nations that are not necessarily member states of CERN, because it was realized at the time that CERN itself would not be able to build a sufficiently sized computer that would tackle the computing demands on the LHC. Instead, what falls on the CERN is really to record the data as they come from the detector, make sure that they are written to tape as quickly as possible, and then fan it out into the world to the various centers. You see here Brookhaven, New York, you see Amsterdam, you see Chicago, Canada, Vancouver, you see Korea, you see Taipei mentioned here. So centers spanning the globe, and the network that was fortunately developed at that time with sufficient bandwidth is used to transfer the data after first zero suppression, if you wish, into these so-called tier 1 centers, where they are stored. One copy at CERN, the other copy then outside, so that universities could engage with the so-called tier 2 centers, still powerful computers or computer centers that would allow the analysis of the data. So this tiered way of computing was new at the time, because what you wanted is that somebody in Tokyo would sit down, log on, and have the entire tier 1 at its fingertips. So you wanted single sign-on to this grid to have the code executed at the best available computing center and free computing center where you could analyze the data. So you see this had a lot of flavor of cloud computing, but of course it happened 10 years before cloud computing became the fashion. This model has been so successful that also neighboring fields of particle physics and astroparticle physics have been using this. So even non-CERN experiments are engaged in this, and this is really the incarnation of big data, if you wish, massive amounts of data, petabytes of data that are crunched with this facility. Now, here's a word on the technology side, and I use a medical application because it speaks to two aspects of what is done at CERN. Accelerator development led to, well, effectively 30,000 accelerators worldwide, and many of them are used for medical purposes, initially cyclotrons, but today, for example, we have proton therapy in addition to X-rays sources, of course. There is a difference between using X-rays and protons, because when you accelerate protons onto a target, or let's say a human tissue, In this medium, the protons are decelerated without losing much of their energy until the very end of when their energy is almost exhausted, when most of the energy is suddenly released. So when the velocity is very small. And this is exactly what you need to treat a tumor, because you don't want to irradiate the tissue in front, which is something that you can't avoid when you use X-rays. And this is the reason why in X-ray treatment, typically several beams are used, which then overlap at the center of the cancer or the center that needs to be put in therapy. So with these proton accelerators emerging, suddenly there's a new tool, which is, for example, of advantage in treating child cancer when you still are extremely careful about the front tissue that sits in front the cancer cell. Now, the next element is you don't want to do this blindly, so you need some imaging. The detectors that have been built for particle physics, in fact, allow to use, for example, positron emission tomography, in which you have a positron emitter injected into the tissue that you want to examine, and with the positron emission, you can then examine in detectors the location of that and actually produce images of this kind, which have high resolution and allow to treat the patient in a very specific manner. The best is, of course, if you can irradiate and observe at the same time, which is a technology that is emerging at this time. Now, in the beginning, I alluded also to education and training, and I have one slide here to show you the scientific program that happens at various levels of education, be it for the scientists at CERN, in which we have an academic training program, be it for the young people, PhD students or postdoc, in which we have an annual school at CERN, or rather 3 schools, named CERN School of High Energy Physics to teach particle physics, CERN School of Computing to teach most advanced computing technology, and of course accelerators to learn about the latest developments in accelerated technology. Now, we also reach out at CERN, we also reach out to the other continents. So we have, for example, an Asian European Pacific School of High Energy Physics, which happens every 2 years. And we have a Latin American School of High Energy Physics, which also happens every 2 years, where eminent scientists go to either Asia or Latin America to teach students about this, the latest developments in particle physics. So this is at the academic level, but of course we all know the earlier you reach out to young kids, the bigger the impact for science. So we have an undergraduate summer student program in which some almost 300 students come to CERN and spend 10 weeks or so, 8 to 10 weeks at CERN to learn about the latest development in specific areas of particle physics, of technology, but also even on administration. So these summer students come to CERN to familiarize with the working at CERN. An even bigger impact one can have when you teach the teachers. So CERN has an active CERN teacher program in which teachers come to CERN to learn about modern physics, which they can then bring home and teach students. And then, at least outside of COVID years, we have some 135,000 visitors per year that come to CERN in busloads to see the sites and the tools used at CERN. So uniting people from all over the world in the quest for understanding science is an important aspect. And I come back to the teacher program in this slide Since it started in 1998 to 2018, so over a period of 20 years, there have been some 12,000 teachers, and they came to CERN either from the member states, which is the vast majority, but some 1,100 or 1,200 teachers also came from afar to take part in teacher programs at CERN, which they then brought back to their home countries. The success of this program really took off in the beginning or end of 2010s for two reasons. One is the start of the LHC, but it's also the start of the time when the teacher program was given in the native language from the country. This, of course, helps a lot if you, well, Norway, even school pupils are fluent in English, but when you go to some other countries, there may be a hurdle of language, and it's a big advantage when you hear the science program in Estonian or Latvian or whatever country you pick. And that led to a huge success of this teacher program. And to give you a feeling for the summer student program, there are some 160 or so from the member states and associate member states, but a large fraction funded through individual and sometimes private programs, again from all over the world, who come to CERN for this summer period. And you can imagine when these 260 to 300 people mix, it's a very colorful mix, both in thinking, in ideas, in education, and it makes up a very fruitful collaboration between these young people. And oftentimes bonds are forged that last for the rest of life. So this is where people are brought together. Now, let me continue a little bit with science here. And I will try to illustrate this a little more. I want to show you some more detail of one of the detectors, the CMS detector for this matter, and to get a feeling for the size of the apparatus. I don't know whether you can read this. The overall diameter is 15 meters. The length is 30 meters. The magnetic field is almost 4 Tesla, and it weighs some 13,000 tons. So it's what we call a compact detector that is presenting so much material of the particles that are emerging from the interaction point here in the middle and then traversing the material where they are stopped, or most of them are stopped. You can look at how it looks from the inside. This is the new beam pipe that was just installed a few weeks ago. The particles collide in the middle, and you see the layers like in an onion shell that is spanning up, where in each layer, the trajectory of particles is recorded, so that after reading it out with a computer, you know where the particles went, and then you can analyze the event. This endeavor has been going on for 10 years and will continue probably for 20 years. Today, we are here in a long shutdown 2, LS2, where the detectors have been upgraded, and you see here in a long shutdown 3 years, where Atlas and CMS received an initial completed the initial upgrade of phase 1, and the 2 other detectors upgraded in a big way. That continues. There will be the operation will resume in the beginning of next year to run at higher energy, and then there will be another installation shutdown, and then it continues probably till the end of the 30s. The whole purpose of upgrading this machine is to increase the intensity. And you see these key figures at the bottom. We call this inverse femtobarn, but never mind the unit. but it went from 30 to 119, 350, and we want to go to 3000 or 4000. This intensity is a figure of merit for how frequent, very rare processes can occur. And that's actually the challenge in the LHC program. And the reason for that is shown here. We have our current understanding of the fundamental interaction is that there are several of these, and I show this in the next slide. The most important for, well, in some sense for our being is the strong force that keeps together the quarks, two up quarks and one down quark in the proton, binding them through gluons. And that's the strong force that holds the proton together. In fact, we know four fundamental forces. Three are put together in the so-called standard model that has the up quark, the down quark, the electron, and its associated neutrinos. And then for some still unknown and non-understood reasons, we have several generations where this pattern repeats with a charm and strain quark, which a priori doesn't exist in nature and has the leptons, muons, and neutrinos as a partner. And there's this third generation, top and bottom. And we don't know why why nature has chosen this way. Then there are so-called gauge particles, the glue of the interaction, the gluon for the strong force, the photon mingling with the Z boson and the W boson for the so-called vector bosons, for the electroweak force, and the Higgs particle that has a particular nature in this scheme because it's a scalar, not a vector particle. Now, here's a summary of the forces, the known forces, the strong force, and its purpose is to bind the protons and the neutrons, the quarks inside these protons and neutrons together. The weak force is responsible for the decay of the neutron. So the neutron can decay into a proton, an electron, and a neutrino. Then there is the light, which we use to see, but it's only a very small part of the electromagnetic spectrum. In fact, the electromagnetic force couples with the weak force to the so-called electroweak force. This has already been unified. And the whole, the three forces, strong, weak, and electromagnetic, form together the forces of the standard model. The gravitational force is of a special nature, and it's excluded from the standard model since it does not couple through a vector particle. Rather, it's a so-called tensor force. And that's the origin of the gravitational waves, which I'm sure you have heard being spoken of recently or over the past 5 years when the first gravitational waves were detected. So with these forces at hand, you can imagine with a strong force, you will have a very high probability of interactions. This is why there are some so-called cross-sections, some particle reactions appearing here with a very high rate. And then when you go down the scale, several 10 orders of magnitude, you have the particles, you have the reactions responsible for the electroweak force appearing here. So you can imagine when you look for these processes, you have to look for the needle in a haystack because you have 10 to the 11 reactions that happen that are not interesting for you. They produce protons, or jets and jets, but they will not produce this. And this is why you need computing tools to sieve out these interesting reactions from the bulk of reactions that may be not so interesting for you, depending on the research you choose to undertake. I've spoken about the vector bosons, triple W production, and mention it here because this is also happening at the same time of the topical conference. Just recently, 10 days ago or so, the production of 3 Ws was announced at the conference. And you can see this, the process is shown here, where muons and electrons at very high energies are emerging, and they are reminiscent of the W decays, and there's a lot of missing energy in these events. So these are the patterns that need to be analyzed and reconstructed to actually detect these processes that are purely electromagnetic in the origin, and that then enable to look further back in time. Now, again, since we are at a conference, we think that protons and neutrons, of course, made out of 3 constituent quarks. We also know of so-called mesons that are produced by cosmic radiation, but it is quite unusual that 4 quarks bind together. And here is one observation where 2 charmed quarks, so particles, quarks of second generation, bind together with anti-quarks of the light generation. Only a few years ago, this was only theoretical speculation, and now these tetraquark and pentaquark, so 4 quark and 5 quark states, have been observed. And this one is particularly spectacular because it contains the second generation 2 times. So that's also a new announcement at the recent conference. And you see how these new results emerge from the science. Now, speaking of the CERN program, I want to allude a little bit to the international aspect of the CERN program, because CERN is also building detectors for a program that's happening or taking place in the US. At Fermilab near Chicago, they plan to bend the proton beam, an intense proton beam, downwards, so that when the protons impinge on the target, the neutrinos that are emerging travel 1,300 kilometers through the Earth, below ground, some 32 kilometers or so, and then are hitting a huge target a mile underground in an abandoned gold mine, where then scientists are ready to record the interactions of the neutrino. And this detector, the massive detector, has been developed largely with the help of CERN. You have building blocks like this, which are 6 meter cube. In some sense, with a fiduciary volume, they're put together like Lego stones to build up the big detector that will be then used at Fermilab. This is the detector development for European scientists mostly working at CERN, so that in the end, the detector can be built a mile underground. And then a completely different topic, but just to give you a feeling for the breadth of science carried out at CERN, is where CERN is producing antimatter. And of course, to have matter, you need a nucleon in the middle and you need an electron outside, except if it's antimatter, you need an antinucleon and an anti-electron, which we call a positron, circulating around the nucleon. And the simplest of that is the anti-hydrogen. And to examine the anti-hydrogen, you want to bring it at rest. So you need all the tools at CERN, namely first produce antiprotons, then decelerate them in a decelerator, capture them in an electromagnetic trap, take some positrons from a radioactive decay, bring it close to the trapped antiproton, they bind and form antihydrogen. And then you cool the whole system by a laser so that basically the antimatter is at rest. Now bring your own bag and you can pick up the antihydrogen and do physics at home. That's the next step, and it will happen in a few years' time. Now, who decides on the scientific program of CERN? well, of course, the member states, so it's the CERN Council. And in fact, it completed a round of strategic planning, which it does every 5 years or so, and came up with some recommendations here, namely, first of all, is to really complete the high luminosity upgrade and operation of the LHC to really extract all the physics one can get out of the LHC and its upgrade that I alluded to. The upgrade for intensity. And this is an upgrade of the accelerator and an upgrade of the experiment. And this will carry out a very fruitful physics program in the 40s. And you see some of the results that I just show as an indicator of the steady physics flow that comes out of the LHC. Now, one also has to think of the future, and there the community settled on a very bold plan, namely to have a Higgs factory to examine the Higgs particle that plays this peculiar role in the standard model of particle physics because it couples to the mass of particles. And now you can imagine that maybe the dark matter that we see from the astroparticle physics couples to the Higgs particle because it's massive. And so we would see some deviations in the couplings of the Higgs particles. And therefore, the Higgs factory has been put as the highest priority by the particle physics community. And it appears in various versions. One is a study that has taken place in Japan, and maybe Japan volunteers to host the ILC, a machine as a Higgs factory. Or CERN examines two concepts. One is a linear collider alongside the Lake Geneva, and the other one would be a future circular collider that may start as an E plus E minus collider in the first step, and then allow to upgrade to a proton hadron machine that would allow to reach a much higher center of mass energy. So these are studies that are continuing to be examined, and probably by 25 or so, in 4 or 5 years' time, we will know a bit more about which of the projects will be chosen or whether Japan moves forward with another project. But you see, because of the lead times it takes to build such an accelerator, the planning has to start now, even though there is a very lively program ongoing already. And that shows already where we have to expand. The other element that I don't want to omit here is the scientific computing, because we've learned that the resolution we gain with the detector can be massively improved by using modern tools of data analysis, like machine learning, which really increases the separation power. And that's what you need resolution of detectors for, to come up with the best signal possible that you extract from the detector. And to continue with a little bit with speculation, but also some real work, CERN has recently launched a quantum initiative, and I'm sure you have heard about quantum computing, but another step is ultra-sensitive sensing, namely detection, building detectors based on quantum sensing. You can also use fast networks built on quantum technology, in which not only bits are transferred as in our network that also use fibers, where light is transmitted to transmit information. But here you could actually transmit entangled states, so communication, somewhat spooky transmission, much faster, and with remote effects that can be detected. and of course, with a laboratory like CERN, quantum theory is already well placed. So this topic of quantum comes in a broadband, and one of the first elements is in fact to create states in which the quantum state can be preserved for a sufficiently long time so that you can experiment and sense that. So this is a new initiative that also happens elsewhere, but I just want to mention it here for completeness. That brings me to the end of my presentation. Thank you for listening, and I'm looking forward to the questions that may arise.
Thank you very much, Eckhart, for this very insightful presentation. We have had one or two questions. Let me start. You mentioned that in this huge accelerator, you're now accelerating elementary particles to very high energies. There's now protons flying through this accelerator ring. And what I would like to maybe exemplify to our audience is there some everyday analogy to understand how much energy is really stored in these particles that are moving around this accelerator ring?
Yeah, so if you take the individual proton colliding with a proton, we take our unit is the tera electron volt. So the equivalent of 10 to the 12 volts of a battery that a singly charged particle would have to traverse. That doesn't help much. It's still not a whole lot of energy. When the two protons collide, the point energy, the density you have there is very faint. However, the energy stored in the 10 to the 10 protons that are in a proton bunch of 30 centimeters or so, and then we have some 3,000 bunches stored around the circumference, that is equivalent to a plane slowly landing or rolling out, so an Airbus or those stopping, so that you can understand the energy stored there can be easily used to melt a block of iron instantaneously. So in short, you don't want to lose the beam of protons, and fortunately that doesn't happen because the magnets keep them on their trajectory. And even if a magnet fails, the magnet cannot get rid of its field fast enough. We still have the time to extract the protons gracefully. So the message is very clear. For our sensing the collision, the energy density into protons is still rather weak, but the density of the energy density of the beams is enormous.
Thank you very much. You also mentioned that at CERN, a form of extreme cloud computing is carried out. And again, you mentioned that this is important to run the current experiments. Can you give us a feel for the gigabytes that are shuffled around there? Would this be something that a usual university network, can a usual university network handle an LHC experiment alone?
No, this is impossible. At the tier 0, I hope you can see this now, the data rates are enormous. In fact, when you look at the front end, we are easily recording with terabytes per second from the experiment. To stream this away, you realize you need special recording devices, and the experiments do this by going massively parallel. reducing the data as quickly as possible to the relevant information. So in a way, discarding the zeros, the noise, so that they really get the signal. And then they are getting down to gigabytes per second. And that's something that you can handle with fast switching and start to stream to tapes for recording. But the amount of data recorded over a year is typically some 50 petabytes. This is the amount of data that already excludes the zero, so it's high density information. And then what goes to the networks is can be spread out over the year. So we don't have to fan out the information in real time. There's some buffering that we can use at CERN. So when the protons are re-injected to the LHC, we have a break of some 2 hours or so, and we can still stream out the data into the tier 1 center. So the storage of and preservation of the data is a formidable task, and it would be impossible to tackle this at the university. Well, unless it's a tier 1 site. And if I mention the Karlsruhe University, it's also the Karlsruhe Institute of Technology. So it's a large center with a massive computing center that is able to tackle the German part in the tier 1 activities. And there are other centers, as you see from this plot. Cloud computing, as we all know it nowadays from the commercial vendors, Google, Microsoft, Amazon, you name it, they are typically used to offer computing power and storage. And what we do here is rather at the tier 2 level, when we have a massive recalibration job or so, we keep the data and make them also available to the commercial vendor. They make available their computing center and bring back the highly condensed data that, if you wish for the experts, it's the 4 vectors that enable us to do analysis. But we do not hand out, we do not hand over raw data, which we then might not get back if a company is bought by another company. Well, that will not immediately happen with Google, Amazon, and the like. But you see, we have an obligation. The research is publicly funded, and we want to keep the hand, of course, on the raw data for time on end, so that if somebody comes up with a new idea of research, the data are available for further analysis. And speaking about this, if I may, for 10 more seconds, open data is something that has become a requirement of the European Commission in funding European research. It's also adopted by national research programs. Even though the detectors are built by the collaboration, after some grace period, the experiments make the data available for analysis by people who, via theoretician in Stavanger, who gets an interest in analyzing some data of CERN.
Thank you very much. These were very insightful views on CERN, its operation, its science, its organization, and the many programs that it runs to bring the scientists of the world together and to strive for a really enormous task, namely understanding indeed the smallest pieces of the universe around us. Thank you very much, Eckhard Elson. It was a pleasure to host you. And at this point, I would like to close for this evening. I would like to remind our viewers that there are 2 more presentations coming up this week. One on Wednesday, August 4th where theoretical physicist Chris Quigg will tell us about symmetries in nature, and on Friday, August 6th, Jongbo Kang will tell us about the strongest force in nature that Eckhart has already alluded to in his presentation today, namely the strong force. Thank you for tuning in, and I hope to see you on Wednesday, August 4th. Goodbye.
Thank you.